introduce you and all that stuff.
So I'll just leave the first slide then.
Yeah. So you can put up the slides whenever you want. I think you can do it. Yeah, okay, you definitely can. So I think everyone knows Lina. If you don't, then you can't see her either.
No, you can.
This is Lina.
This is my voice. This is good enough.
Yeah. So Lina's going to be talking to us about Prodsimplicial and p-path complexes in directed graphs, which is presumably work you're doing with Natasha, or you're doing it with Margarita, or none of the above.
Okay, so this bit I'm doing with Dr. Dr. Saito and Margarita.
Okay.
This I just read, and I'm trying to make sure the whole point of this talk was to make sure that this doesn't match this. Otherwise, I'm reinventing the wheel, and that's a waste of time. Turns out it's not. So, spoiler alert.
All right. So, well, you can start whenever you want.
All right. So in that case, I didn't know who would be here, so I have a couple slides on regular old simplicial homology as a kind of review, but if everyone's comfortable, we can skip over those. At any rate, outline is going to be regular simplicial homology review, so that we can compare to the Prodsimplicial homology, which is one way to expand on that definition. Then we can go over p-path homology, which is a different way. Sorry?
John, I think your microphone's on.
Yeah, I joined with my phone and I'm trying to find the mute button right now. Sorry about that. Give me a second.
All right. So regular homology, one new homology, second new homology, and then making sure that they are not actually one and the same. That's the outline for today. So starting with regular old simplicial homology. Review, simplex is any term in this kind of sequence, so it's just a general version of a triangle, depending on which dimension you're in. You usually just create them going up in dimensions by adding one more vertex and connecting everything to that vertex and making it a solid in whatever dimension you're in. So these are usually completely filled in. In most applications, especially when they come up, let's say in topology qualifying exams, you're using triangles or you're using simplices to approximate other things, and they have a geometric meaning. So like when you triangulate other surfaces or manifolds, you're using simplices because they make the computations easier. However, I want to deal with abstract simplicial complexes, which is when you don't so much consider the geometric meaning, but just the collections of points. So I'm going to define just the bare bones of what I need in order to make homology groups make sense. To begin with, I need an abstract simplicial complex. It's just going to be a collection of subsets of a finite set, such that for any even if it's empty, it's just closed under inclusion. So any subset will be included. And like I said, these subsets can be given some kind of geometric meaning, so I can interpret every singleton like it's a single vertex. I can interpret pairs like it's an inch, triples like it's a triangle, and so on. So I always have one more element than the dimension of the simplex I'm in. And this lines up with the previous example. For example, in this picture, which I will have in the next slide, I can actually describe a simplicial complex that includes this triangle, so that's here, all of the edges, which are here, all the vertices, which are here, and then because I have to be closed under inclusion, I also include the empty set. And that's it. That's an example of a simplicial complex. The inclusion property is going to be important, and I'm going to be seeing similar versions of this inclusion property for the other complexes I'm going to define. This is just groundwork. This notation is kind of standard, and also keep it in mind because the collections of points define my basic cells, so the building blocks for the boundary operator, which is coming up next. Boundary operator acts on things that are called n-chains. So I'm not just living in a set of simplices, I'm living in this space, so a linear space of linear combinations of simplices. And those linear combinations are what I call n-chains. In homology, you're going to be interested in the boundary operator, which acts on this set, and then you're going to be looking at the image and the kernel. So boundary operator, as it is defined traditionally for simplices, what you do is you consider the simplex generated by all but one of the vertices, and then you do this alternating sum over them. So I'm not including an example. I'm assuming that this is a straightforward definition that everyone has seen in their topology textbooks. And this just happens to be an important property for the boundary operator to have. If you compose it with itself, you should get the 0 map. This should hopefully all be reviewed, but if anyone has questions, we can go back to this. I just want to have something to compare to, since the other two complexes are variations of this one. Questions so far?
Not yet.
Crickets? Okay. So, new complex, Prodsimplicial homology. If I were to look at a graph, an arbitrary graph, it literally only has dots, so vertices and lines, edges, and as I defined them earlier, if I look at them under the lens of the traditional simplicial homology, I only have 0 cells and 1 cells, which is not very interesting. So in order to see higher dimensions, we need to redefine what your building blocks are. So we can't be looking at it like it's just 0 simplices and 1 simplices. I have to define a new thing that's not a simplex for me to look at. Also, because of where I started looking into this homology in the first place, I'm going to be focusing on directed graphs. The background is biological and not super relevant for this talk because I already have too many slides. But suffice it to say that I'm interested in processes where the direction of the arrows matter. So I'm not really going to worry about the undirected graphs. And all of the groundwork uses that extra bit of information. So in particular, what I'm interested in, at least biologically speaking, are converging paths of this kind. So if I have multiple paths that go from one vertex to another, and all of these subgraphs that have one source, so a node where all of the edges are outgoing, and a target where all of the edges are incoming, I'm going to call them consistently oriented. I also explicitly want this to not have any cycles because it is conceivably possible for me to have something like this, which has a source and a target, but it also has a cycle right here. So I don't want this, which is why I require it to not have a cycle. I can make a variation of a simplex so that it is directed and it also is consistently oriented. All I have to do is follow the traditional construction of adding one vertex and all edges pointing to that vertex. And automatically I will always have consistently oriented graphs. So point out that whatever starts out being the source target, the source vertex, so for example, this one, stays the source vertex, and whichever vertex has been added becomes the target vertex. So this is the one that's being added, this is the one that's being added, this is the one that's being added, and all of the edges always point towards it. More importantly, if I were to think of this as having labels, for example, on the vertices, say 0, 0, 1, 0, 1, 2, I can induce a total order based on the in and out degrees of the vertices. And that total order means that any subset of this will also be a directed simplex. So if I were to kill this vertex and I have this edge, this is still a directed simplex. If I kill this vertex, then I still have this triangle, which is also a directed simplex. So that's an important property to have, especially when we talk about complexes where I want to be covered by inclusions. However, if I just assigned a direction to regular simplices, I wouldn't be doing much. So let me introduce Cartesian products of graphs. They're called Prodsimplicial, because they're products of simplices. Cartesian product is obtained by doing the regular Cartesian product of the vertex sets. So that's here, and associating edges according to this rule, which I think is better explained in the example that's coming up. But for now, I'm just going to point out that this operation is up to isomorphism, associative, and commutative, so it's a nice operation. And moreover, it preserves the consistent orientation property of graphs. So example, so that we can understand that rule. What I should have is a lattice, let's say, of vertices corresponding to the Cartesian product of these 3 vertices and these 2 vertices. So that's all these 6. And then for each appearance of this graph, which will be associated to each of these vertices. So I'll have basically this graph times this vertex, which is this copy. I'll have edges connecting the copies of this graph. Same here. I'll have one copy of this graph associated to this vertex right there, and I will be connecting them. So the fact that it's a copy is signified by the fact that these second coordinates are the same. And so if AB is an edge here, I should have AX, BX as an edge there. And then I do the same thing with the first coordinates, where if I fix the A coordinate and YX is an edge here, then it should be also an edge on the product. With all those nice properties in mind, I can define a Prodsimplicial cell, which will simply be the Cartesian product of directed simplices. On this, with this as my building block, I would like to now define what the cells will look like. Here are examples. Geometrically, they seem to match intuition for polyhedra. So I can see in 3 dimensions, we have triangular prism, we have cubes and hypercubes, and then we just have regular old simplices in all dimensions. But essentially, it allows for a richer structure than just simplices, right? Because these are I can triangulate them and turn them into simplices, but it admits for more things to be filled in. So Prodsimplicial complex, I have to tweak the definition a little bit. Is inclusion and intersection don't work exactly right. But if I just make it so that the union, essentially what could happen is I could have a square which is connected to also a square along these 2 lines. But unlike when I have a triangle fixed to another triangle, this edge that is connecting the 2 triangles is also a simplex, but this pair of edges is not really a simplex, or it's not really a Prodsimplicial cell either. It's just in the union of the faces of the 2 squares. So I need to tweak the definition of complex slightly to accommodate for that. Otherwise, still more or less following Simplicial homology. I should probably point out there is a book. So this is the Combinatorial Algebraic Topology by Kozlov. This is from 2008. I was first pointed in the direction of this book when I started looking at these figures, let's say, because all we had in mind is that we wanted to consider filling in triangles, squares, in similar graphs. And then someone told me, hey, these look a lot like Prodsimplicial cells. So I start looking into it. This is the only reference I can find. And it doesn't really develop the theory. It just has a little 2 or 3 line excerpt. It's mentioned in a miscellaneous kind of chapter, and then is never mentioned again. So if anyone knows references, I would be welcoming those references. Otherwise, I'm developing theory because as far as I can tell, it's not really developed. So now what would the cell complex in a graph look like? Again, at first glance, this just has vertices and edges, but I can start associating a complex if I look for Prodsimplicial cells. So degree 0, there's nothing interesting, just the vertices. Dimension 1, ignore the vertices and now look at the edges. The direction is included. In 2 dimensions, then I can start filling in these 2-dimensional figures. So the squares that are consistently oriented, exactly as I define them as products of edges, are included. That is also all of these square faces on the cube. That is also this triangle, but note that this triangle over here is not included because this is a cycle. Since this triangle is not consistently oriented, I do not include it. And if I go up one more dimension, I notice that this cube is actually a consistently oriented cube. It is a Prodsimplicial cube, so I also fill it in. I do indeed have a solid cube, three-dimensional cube in this graph. Now that I have proper building blocks, I can define a chain. Same as before, it's just linear combinations. And here is an example of what a chain might be. You will usually use chains in homology theory, going around in cycles to closing paths like this. And it will represent going forward on E1, so positive E1, against the direction of E2, so negative E2, against the direction of E3, so negative E3. But this kind of expression is what we're looking at. The boundary operator, I can define it on simplest exactly the same as before. But more interestingly, I can expand that definition using something similar to the product rule for derivatives. So since I have a product of simplices, I will use a product rule where I do the derivative on the nth term by not deleting the nth term in the product, but boundarying or applying the boundary operator to the nth term in the product. All right. Proposition, same as before. I can prove. Oh, sorry.
Could you go back? So the notation with the bar, okay, I see. I just had to read the bottom. So the notation with the bar means that it's the whole product still, it's just you take the boundary operator to the nth term, or the ends of ith term.
So
okay.
Instead of killing this term, what you do is you do the boundary of this term.
Okay, that makes sense.
And then if I use a definition with an adjustment on the indices, so the traditional way of doing this exponent is to just count the vertices of the simplex. And this is more or less doing the same thing. It's just counting how many vertices you've had in the factors up to that point. So it counts the vertices of the factors before, plus whatever point in the simplex you're working on you are. And I can't English, but hopefully something there made sense. This is still using the principle of counting how many vertices you've used up so far in the product. And as defined, this will satisfy this property still. So we should be good. And now I can introduce the exact same concepts with p-paths. So fair warning, the definition taken from some papers is kind of convoluted because it basically needs a lot of adjustments. I can start with a definition of a path, but then things don't work perfectly unless I mod out a lot of things and restrict a lot of things. So please ask questions if it's not clear. I know I had to read and reread, and even then I left some things out. From the beginning, if I just consider a graph, an elementary p-path, so any kind of path, the most arbitrary kind. In theory, I'm not going to care about the edge set in the beginning, so I'm just going to allow any sequence of the vertices with p plus 1 vertices to be an elementary p-path. And then when I do linear combinations of those, I call them regular p-paths. So elementary, anything at all. Linear combination, p-path. However, I'm not going to be working with p-paths, and we'll get to that in a minute.
So just to make sure I understand, so it has nothing, I mean, there may not be an edge connecting those two vertices, it's just...
Correct. So essentially, there's going to be a lot of missing edges, even if I try to make it so that the allowed edges are the ones that, so that the allowed paths are the ones that consider those edges. And even then I could be missing other things. So I'm not going to worry about this requirement just yet. I'm putting it in just so that we can work on graphs, but I'm going to need to rule out a lot of things later.
Okay.
So essentially, even though I'm defining the elementary paths, and this is going to be important, just anything, and the combinations of paths, and this is going to be important, but I'm not using them just yet. I have this space, lambda p, but I'm not going to be working with lambda p. I'm going to work with some derived version of lambda p.
I have a question about
Mhm.
what is a linear combination?
Oh, so linear combination, just any sum. Suppose I used this notation. Oh, the
This is a sequence, right? So
yeah. So I0, I2, I1, etc. plus beta e. This could be J0, J1. I don't know why 0 is being followed by 2, and so on.
So formal sum of p paths.
Yeah. Fix a
With-
field, any field. Usually it will just be real numbers, integers. Well,
update
field, but
integers or
yeah, integers doesn't work as a field. They say to fix any field. Without loss of generality, you could probably say R,
okay.
but you will usually end up using integer coefficients.
Mm.
So all these formal sums where they choose this notation for their coefficients. So example of path complex. I'm defining the path complex on the very general paths that I'm not quite going to be using. But that just so I can say that the path complex is closed under inclusion where any sequence from 0 to p being in the complex implies that the subsequences, so if I trim off the first vertex and the last vertex, those subpaths are also in the path complex. So this is the equivalent of being closed under inclusion, let's say in the abstract simplicial kind of sense. Anything I kill from an abstract simplex has to still be a simplex, and it also has to be in the simplicial complex. In this case, if I kill the beginning or end vertex of any path, so I'm not really allowed to kill anything in the middle. But every time I trim from the ends, those subpaths have to be in the complex, and I say that anything in that complex is an allowed path. So, for example, I can associate to a simplicial complex like the one I had in the very beginning, a path complex. So I can make a direct relationship between the two. It's not the only way of making the path complex, but it's one way that would allow some kind of geometric interpretation. So I can let the 0 paths, so the paths that don't really go anywhere, be the vertices. The 1 paths are going to be the edges. And then this filled in triangle will be this 2 path, which would technically be this, from 0 to 1 and then 1 to 3. However, this is not the only way to generate a path complex. I could also choose to add this path here, and this would still be a path complex. So depending on what I call allowed, depending on what I define as my path complex, I can change what I'm the sets and the spaces that I'm going to be doing the math with, and that's going to be important in like 2 slides. So I can do it directly from simplices, and I can do some kind of equivalence, and there are propositions about when a path complex corresponds to a simplicial complex, but you can also expand on it so that it doesn't exactly match a simplicial complex. Boundary operator uses the same principle as before. And this is what I'm going to be using to restrict the space that I work on. I need to make sure that the boundary operator makes sense in every circumstance, especially when I do it multiple times. But in order to say that I'm restricting based on the boundary operator, I need to define it first. Definition will be deleting 1 vertex at a time from the sequence of vertices in the path. And then depending on the position where that is in the path, then that's going to be the coefficient, the power for -1. So similar notation, also little hat notation, say that I'm killing 1 vertex at a time. And here's an example. It actually doesn't disagree with what I had earlier. If I wanted to do boundary of this path, which corresponds to this triangle, it works out the same. It's forward on this one, which is this positive one, backwards on this one, which is this negative one, forward on this one, this positive term. So even though the path as a cell, technically the only cell here is this path, I can still kind of see as a triangle or as a simplex. Now, once I fix an arbitrary path complex, so once I've decided what is allowed, I consider the set of linear combinations of those paths AP. Those elements are going to be called allowed paths, and they're still not really what I'm going to be working with. So for example, I could run into this kind of situation where I have this path, but I do the boundary, just like I did before, and one of the terms doesn't exist in the graph. This is where I start to worry about the edges existing or not existing between the vertices. This is not allowed. And so I wouldn't want to do boundary of this because I'm going to run into trouble. So what you do is you define the set of things where this is allowed in the previous dimension. And these are going to be the delta invariant paths. This is where you're actually going to be computing the homology groups. So in a couple slides, we're going to see this come up again, because this shows up in all three cases. And I could think that I'm in trouble because this is a 2-path, this is a 2-path, but when I do the boundary for a 2-path, just like here, I'm going to be missing this edge, and that could be problematic. But as long as I use linear combinations and the appropriate linear combinations, I can still make it work. I just have to make sure that I appropriately define this set to be working on. So before I move on, maybe questions.
I have two, I think, or maybe it's one,
Yeah.
I'm not really sure. So this boundary operator thing that you've defined,
Mhm.
so squaring it gives you 0 for on these omega p's?
Correct.
Okay. If you
Oh.
did,
It should have that on a slide, but apparently I forgot it. Yeah.
so okay, that's okay, good. If you do the boundary operator on, so you can take boundary operator of something in AP, it doesn't make sense, and it may not live in AP -1, yeah?
Correct.
So you can't take boundary operator, or does it make sense to?
Essentially you can do it, but only once. So if I do this example, then what are the 2 paths? The 2 paths are 0, 1, 3, 0, 2, 3, and I can do the boundary of those. Um, 0, 1, okay. And I can check here. Two, 3. And for example, which one is missing? This one is missing from this list. So here I could be in trouble if I try to use A2 equal to, was generated by, wait, 0, 1, 2, 3, yeah, and 0, 2, 3. So what I have to do is do something like consider an arbitrary linear combination of these things. Do the boundary of this and see how I can make this be in this in the generated set by these two things. So maybe I'll just copy this. There. So if I do, I should end up with 10 alpha times this, because it's a linear operator, so I can just do this. Beta times this. And the unpleasant term, which is this one here, I would like to see it cancel out. So what I have to do is make sure that the coefficients are such that these two terms cancel.
Let me see. So
And what I could do is do omega 2 be E013 minus E023, and then everything works out.
I see. Okay. So that's careful. Okay. Okay.
Yeah, so the construction is kind of obnoxious in the sense that it's a lot of tweaking to make it actually work. But that's why it takes so long to set it up. So hopefully that example kind of works.
Yeah, it makes sense.
Was that the second
Is
question?
this
Yeah,
is
kind of
this
combined.
equivalent? Oh,
Sorry?
is it equivalent to like add one more edge to 0, 3 on the graph?
Oh, sorry. I could just work with a different graph, but the idea is to work with the existing graph and just define this omega set to work. It could be that I have to let the omega set be 0, and then that's fine. It means that homology groups later will just be 0 from much earlier on.
Yeah, I think this graph can be reduced to the standard Simplicial. But I don't know. It's kind of weird.
So that was sort of my question, I think, because there's two kind of options I see.
Offset edge, which is
Yeah. So I think my question, I think, is the same, or my question, I think, was the same as yours. But I think that made it clear. So if you take, there are kind of two ways to fixing the fact that D doesn't map AP into AP minus 1. You can either enlarge all of the APs, or you can shrink all the APs. So enlarge all the APs so that your definition of AP now contains everything. And so these do include each other, but then you're changing the graph.
Exactly. So without changing the graph, what you have to do is restrict. So you're cutting down instead of adding.
I see. Okay. Okay. That's clear.
Any other questions? No? Okay. So in that case, we can start comparing what the homology groups look like for both types of complexes. So quick reminder, for the homology groups, I'm going to be looking at the kernel of the operator by quotiented out by the image of the operator. Technically, this should split into two things, rank and torsion group. The torsion group almost never comes up in what I'm doing, so we're not going to worry about it. It is totally a thing. It's just not really coming up. I'm most interested in this ring because it counts the number of holes that the space has. And holes are something that you can use as an invariant to compare whether or not two things live in the same space. That's ultimately what I'm interested in. I want to be able to do two graphs, compare them, and say they may or may not live in the same space because they have the same number of holes or different numbers of holes. For example, if I look at basic building blocks of two-dimensional Prodsimplicial cells, triangles, and squares, I know that they are basically homomorphic to disks, right? I'm supposed to fill them in. I define them as being the filled-in figures in 2 dimensions in Prodsimplicial homology. And so these are their homology groups. This just tells me that they have exactly one connected component. I can kind of eyeball that. And I can also see that they have no other holes otherwise. So all of the other homology groups are trivial. If I do the same computation for the triangle, this one I did completely by hand with this path. All of these edges actually work out, so all of these things are fine, but it turns out that this is just Z, this one is trivial group. And if I do the computation with this, which is a little bit more careful and that requires computing the omega and the A sub 1 and 2 more carefully, I actually get the same result. So both homology groups will get me this for the triangle and the square. And if I were thinking of generalizing that result, as far as the triangle being a simplex and this being a cube, I can. It holds in general for directed simplices. So those are always going to be trivial, starting with n equals 1. And the same holds true for hypercubes. So all I'm doing is citing the result in the papers I read, their equations and theorems. And as far as the Prodsimplicial version of it goes, I can just do it because of the definition of the cells. Clearly, the directed simplices are, of course, simplices, so they are cells, so they are filled in, so they're homeomorphic to filled in disks or balls, and the same with the cubes. Where they start to disagree is in things like cones. So a cone as a graph is defined by starting with the graph G. So in this case, I start out with the square that's at the base. I add a new vertex and then connect everything to that new vertex. That is the cone of the underlying graph, which is my square. In the paper where they explore path homology groups, they consider that the cone of something that is filled in my case, the square, will have the same homology groups as the square. So it should also be trivial, starting with n equals 1. However, if I look at this like it's a Prodsimplicial complex, then I would have filled in faces for the triangle. So this is filled in, this is filled in, this triangle is also filled in, this triangle is also filled in, the base of the square is filled in. However, the space inside is not filled in. So this is a hollow pyramid. And because it's hollow, it should have a non-trivial H2. So this is one example where the homologies disagree. This is where I realize I'm not actually reinventing the wheel, and they are indeed different. But this is not the only example of disagreement. There are things called suspension. So essentially it's like a double cone. If I start with an underlying graph G and then do 2 vertices and I point everything towards those vertices, that's the suspension. Here it also fails. And the other place where it fails is because they start allowing pretty much any kind of path. The path that does this, so if I had A, B, so this kind of path, for them it's allowed. In my case, this would be considered a cycle or a hole. So in their case, these are filled in, whereas in my case, in the Prodsimplicial case, these are left empty. Possibly it would be worth finding out what other kinds of graphs the different homology groups disagree on. Because what I'm gathering is that these types of graphs have a slightly skewed kind of symmetry. So the Prodsimplicial cells are slightly symmetric. And these, let's say the cones and the suspensions, if I had to guess, seem to introduce more asymmetry. Maybe that's why. Maybe it's completely unrelated and it's just a coincidence. So it may be worth finding out where else they disagree and why. I think that's my last slide. This is just saying all of these places contribute money so that I can do work like the one I presented today. All of these people helped in some capacity. So that's pretty much all I had for today. Maybe I went a little bit fast, but I was worried that with 46 slides, I would take too long. Questions?
You got through it. So let's thank the speaker first. I still don't know, like it's never gonna be not uncomfortable doing that.
No, little clap button, but I don't think it's any better.
Yeah. What happened? Is there a clap button?
Yeah, there's a clap button.
You have to set this at the beginning, but you didn't do that, I think.
No, I wasn't paying attention. I just updated Zoom, so something changed. So any questions? I think I have like maybe one.
I have a question.
Let me ask first.
You want to ask? Okay.
So what is analog of cycle in dimension 3? Is it
Cycle 3 for what kind of complex?
for the oriented one? Like you have a like the triangular, you have a cycle, it's very clear, but is there anything in like
Or Prodsimplicial or path complex?
path complex?
So in path complex, the cycle groups are the, sorry, I always have to look at this. Cycle groups are the kernel. So what else is going to zero out the boundary?
Oh. Okay, I see. Okay.
So without doing a bunch of computations by hand, I wouldn't be able to tell you off the top of my head.
Yeah,
But
yeah.
yeah,
I want
usually
to
the-
like a picture. Maybe.
cycle over boundary group,
Yes. Mm.
right? I should probably make this look like a C. Otherwise, it looks like I can't spell, and I can't spell, but also.
Yeah. Yes. Got it.
Other questions?
I think I had a question.
Mhm.
So you could, given two simplexes, you can construct a new one using this prod simplex operator. Is that
Correct.
And can you still do homology with this new prod simplex?
So because the simplices are my cells, then prod simplices are also cells. I just get a new version of something that is homeomorphic to a disk or like a filled-in ball.
But can you still construct homology groups from this new simplex?
Correct. So the idea is that if I look at the complex, I'm identifying new things. If I looked at this picture, where is it? Here. And I only look at it, let's say as a simplicial complex, then geometrically, I would only be filling in this,
Mhm.
and everything else stays exactly as it is. A simplicial homology, if I use only directed simplices, would not recognize these squares as being filled in, so it will treat them like holes. What I'm doing is I'm saying allow more than just the simplices to be recognized as solid. In particular, it will recognize the squares, and it will also recognize this three-dimensional cube as being filled in.
Oh, okay. So you're using, you're constructing a different. So you're not doing vanilla homology groups. It's different.
Correct. So I'm basically expanding on it, but I'm expanding on it in two different ways.
Okay.
One way to add more kind of polyhedral-like structures, which are these products of simplices. And then the other way is to go the completely abstract way, just use collections of vertices, but treat those collections of paths on the graph. So I'm still using the underlying structure of the graph.
Okay. But I think my question was if you could write these new homology groups as direct sums of the original homology groups of the original simplices. But I don't know if that's known or if that's sort of
I
a
haven't tried it. I suspect that there may be no relation just because I'm filling out different things.
Okay, sure.
So you're saying if you take two prod simplicial complexes and put them together, or whatever that box operation is, and you compute homology group of the new prod simplicial complex versus the individual ones?
So I wouldn't do Cartesian product of the complexes. I would do Cartesian product of the two simplices to make a new cell, which is one of the items of one of the elements in the complex.
I see.
Right. So I say a cell, a one cell is this, another one cell is this, and if I do the product, I get this square. But the complex itself, the two cells are these squares. So I wouldn't do the product of square by square that are here. I would have some kind of library of what kinds of things are. So maybe I'll do an example here. If I wanted to do all of the, let's say, three-dimensional cells, what I have to do is partitions of 3. So I can do 3 as 3, 0, 2, 1, 1, 1, 1. So this translates into this, and this. So this tells me that the three-dimensional cells are a tetrahedron that is consistently oriented. That's this one. The product of a triangle with an edge, which is the triangular prism, and the three-dimensional cube, which is this one. And so what I'm going to be doing is in my graph, I'm going to be looking for instances of these three things to put in the I guess in the chain group, because they're going to be generated by linear combinations of these three things. But the product happens here when I'm trying to figure out what the cells are, not after I have a complex. Like I wouldn't do product of this with another complex.
I see. So it doesn't really lead to another question, but I have another question.
Mhm.
So it's essentially, these are all just methods of building certain kinds of homology for graphs, yeah? And
Correct.
of just specific kinds of graphs. These directed graphs which have a target and or a source and a target, yeah?
Mhm.
So all of the homologies, I think that there's two, yeah? Or I mean, I guess there's three, but the two relevant ones that you introduced at the end,
Mhm.
they are both constructible for such a graph, yeah? Like any
Correct.
graph, any such graph.
Yeah.
Okay. And then I had another part to that question. I have to think about how to say it. Give me a second. Hold on. Does anyone else have a question while I'm thinking? Okay, so maybe like I think my question is this. So first of all, the two homology theories don't coincide.
Correct.
Do they detect? I mean, I don't know what kind of things you would want to detect in these kinds of graphs, but do they detect different things? Well, I guess like some particular aspect of the graph that you're interested in.
I mean, define well.
I don't know. I mean, does one detect something or detect differences or something like it has a certain number of cycles or certain number of I don't know what kind of things you look for in these graphs. But
So
is
the
one,
way I look at it is, it could be that you're running a bunch of tests, and under one test, you're going to think that there's no difference between the graphs, or at least there isn't that kind of difference. And under the other test, you will find that there's a difference, which is how most topology tests work.
yeah, how invariants work.
Yeah. So
there's no,
it's
like, any-
offering variety on what to test.
I'm trying to think of a good. So for example, it's not a homology example, but in knot theory, Jones polynomial is conjectured to detect the unknot. Is something like that? No, like I don't know what. Again, I don't know what kind of structures you're interested in these graphs.
Okay.
But
Um,
one is not a refinement of the other, so they're both distinct. There's not like one is a subset or inclusion of the other. But do they
correct.
detect like something? I don't know. I don't know what you want to detect is the issue.
I can't say that I have a very good answer because the biological motivation is you have different graphs, and the graphs are associated to recombinations of different genes, and you would like to know whether or not the genes are being recombined in a similar way. So you're grabbing two things and saying, are they similar, yes or no, in this way?
I see. So the question of whether or not it detects something is less important than whether or not they're just the same or not. Yeah.
Correct.
Okay.
So I'm not specifically looking like, oh, I want to know how many of these have 2 holes versus 5 holes, or whether it allows a particular construction of, like, for example, for the p-path paper, they construct graphs specifically to have particular homology groups, just to say that it doesn't eventually zero out, because I suppose it's something that could have been an open question. So they can construct graphs with arbitrarily large homology groups in any dimension.
I see. And there's no. I'm assuming just based on the fact that you're still doing this, there's no classifying object. Yeah. Like.
No, not at the moment.
And is it conjectured whether or not there is, or?
No, not really. I hadn't thought about it.
Okay, that's just
Yeah, open question.
Okay, cool. So I think that's all my questions. Does anyone else have any other questions, or? If not, then let's thank our speaker one more time.
All right.
And any volunteers for next week? John, you want to talk? Alice? Louis?
I'm not sure about next week, but maybe next 2 weeks, I'm guessing.
2 weeks from now? Sure, okay.
Yeah, I think maybe 2 weeks from now I should be able to
All right, we'll put you in.
put something together.
Sure.
Yeah.
So we'll hold you to it. So we still got to find a speaker for next week, but I think we can talk about that later today for now.
Yeah.
So let me stop recording.